Let's get started. So, have you complete the call map stuff? You passed the call map test? You? Yeah, your partner was here yesterday. Yeah, she said, your partner was here yesterday. She said you passed the call. And you guys? Yeah. So, today we're first gonna do a recap on the call map stuff. Then we continue introducing the MIPS virtual memory architecture. Then we talk about the page table design and user address space design. So we all know that call map is responsible for manage the physical pages, right? It's basically, call map is basically a data structure plus two set of interfaces. The data structure is the array of call map entries where each entry represents a page. The interfaces are divided into two sets. The first set is for kernel. We have allocated K pages and free K pages. Here the K stands for kernel instead of allocated K number of pages. The number of pages is actually passed in as the argument, right? So it's responsible for allocating free kernel pages. And this is for the first stage, which is the call map stage, right? When you finish the call map stuff and you continue on the user address space design and implementation, you may want to come up with another set of interfaces, which is called page alloc and page free. This is for the user pages. So what's the difference between the two? So first, allocated K pages. So suppose you are called, the caller want to allocate 4 pages, right? These 4 pages has to be continuous, physically, right? Both physically and virtually. And I will explain what's the difference between physical and virtual address later on. So the difference between the allocated K pages and page alloc is that page alloc, we always allocate 1 page at a time. But allocated K pages is possible that you need to allocate multiple pages and multiple continuous, physically continuous pages. So that's the difference between these two set of interfaces. Other than that, they're quite similar, that this is responsible for allocating some physical pages, and this is responsible for freeing them. Okay, so this is the call map concept. And here is the physical memory layout in the booting up process, right? So before the key main is called, before the kernel start executing, the kernel has to be first loaded into memory to be executed, right? So this part, so the kernel will be loaded into memory starting from 0. Suppose we have 512 kilobytes of memory, so this will be physical address 0. This will be physical address 512 kilobytes. And this part is for the kernel, either kernel code or kernel data. So anyway, it's kernel image here. And in the booting up process, various kind of boot up procedures are called. The very first of them is RAM bootstrap. The function of this procedure is to figure out how many physical memories are there and what's the first available physical address, right? So after this function, we have 2 values, which is the first physical address and last physical address. The last physical address is basically the physical memory size. And the first physical address is basically the end of the kernel. That's the first available physical address, right? So this is before RAM bootstrap or just after RAM bootstrap is called. This is the physical memory layout. And we know that after RAM bootstrap, there are a bunch of other bootstrap functions like thread bootstrap, kprintf, or console bootstrap. And in that functions, they may call kmalloc, right? Which will in turn call allocated K pages. But at this point, you don't have allocated K pages set up properly yet. So allocated K pages will just call RAM steal memory, right? And this is RAM, what RAM steal memory does is just basically forward this first physical address. So whatever is left here is called stealed memory. This part of memory is allocated by RAM still memory. Okay, so at the end of booting up procedure, there is one function called VM bootstrap, which you need to write to initialize your virtual memory. Before this function is called, this is basically what the physical memory looks like, right? The kernel is still here. This part is allocated by RAM still memory, and this is the first physical address, right? So inside VM bootstrap, you may want to call RAM get size to get these two values. Right? This value told you how many physical memory are there, and this value told you what's the first available physical address. Okay, so you may want to allocate your call map right after this region of sealed memory. So first to allocate a call map, you first need to figure out how many physical pages are there, right? That decides your length, the length of your call map. So to calculate how many physical pages are there, you can do last physical address divide page size. In this case, if we have 512 kilobytes of memory divided by 4 kilobytes, which give us 128 pages, right? That's a number of pages. So suppose you know the size of one call map entry and multiply by 128, that gives you the size of the call map, right? Then you can forward the first physical address from here by that call map size, and the call map pointer will point to here. So this chunk is your call map. Now at this point, this is the first available physical address because this part is all used. This is used by kernel, this is used by somewhere else, this is used by your call map. And inside the call map entries, as I just mentioned, there will be one entry per physical page, which means that even though the first page is used by somebody, we still give it an entry in the call map, because call map is supposed to manage all the physical pages, right? Actually, it's one of the design choices here. This is what I suggest you to do, is that map every physical page into call map. So in this case, suppose this used part in total is 4 pages. Then in the call map entries, when we initialize them, the first 4 entries will be marked as used or fixed because it's used by kernel or some other kernel functions, right? Others will be marked as free. So this region mapped to the first used entries, and this part mapped to the unused call map entries, right? The advantage of this mapping is that there is the mapping between the call map entry index and the physical address can be calculated very easily. It basically can be calculated in using this formula. So suppose we get a physical address, we can divide it by page size. So physical address divided by page size is the index into the page call map entry, right? On the other hand, suppose you have an index, you can just multiply that index by page size to get the physical address, right? So it's all starting from 0. There will be no initial offset. That's one way to decide the mapping between the physical page and the call map. Another way is that because this part is used anyway, you can choose to ignore this part and pretending that your call map just manage this region of free memory. That's another way. So in that case, suppose this is the first available physical page, then this physical page will be mapped to the first call map entry. That we also do. In that case, the mapping between the physical address and the call map index is a bit complicated in that you need to add the offset every time you do the translation. Okay, that's another way to do it. So it's totally up to you to decide the mapping between the entry and, yeah. What do you mean? Which part?
As in, the core map entry would not contain any of the pages that have that kernel space. Can that be done?
You mean the second approach?
The core map will only map entries from the first address to the
Yeah, that's the second approach that I mentioned.
not from 0 to the last address.
Yes, that's the second approach I mentioned. You can start mapping from this page instead of from 0. Yeah, you can do. That's the second approach. Either way, you need to but either way, you need to figure out the mapping between the core map entry and the page itself, right? Yeah, you can feel free to do that. Yeah. In that case, you may save a few core map entries. That's it. Yeah. Any questions on this core map allocation? Yeah.
What's this field region before the core map? I didn't follow.
This part?
Yeah.
So if you look up, if you take a look at the boot function, do you know that function in KMan? It will call various kind of boot up functions, right? So the function called is ram bootstrap. This is basically this. But after ram bootstrap, because at this point there is no call map yet, if kmalloc is called, it will call ram steal memory. What ram steal memory does is just forward this first physical address, so eating up the free physical memory, right? So when you get it all the way down to VM bootstrap, which is the last function get called in bootstrap, you will end up have some memory stewed, right? So if you call ram get size, first physical address will point to this. Right? Yeah.
Is there any drawback to just moving VM bootstrap earlier?
I'm not sure actually. So
That's basically what we did.
inside VM bootstrap, you may want to, I don't know, it depends on the design. If it's okay, it's boot up, then it's okay, right? But what I worry is that in VM bootstrap, you may call some other function like lock create, and I'm not sure if at this point you can call that, because if you don't have that part initialized, then that may potentially cause problem. But so far, if you don't have a problem, then feel free to do that. Yeah. Yeah.
So when we call, so is that kernel memory now permanently in physical memory? Like the
This part?
stolen and the, yeah.
This part I think is yes, because it's kernel code and static data.
Okay.
Yeah, it's there. It's not kmalloc. It's
So
not
when
allocated.
we came out, we put everything to the left or to the free part of the clone.
Yes, yes. Actually, this part is allocated by kmalloc and potentially can be freed later on, right? It's just that this part is stewed. If you using the first approach, in which the compact entry map every page, then it's possible that later on somebody is called carefree on this region of memory. So it's possible you end up get some free pages, extra free pages. Yeah.
It could be a problem if someone calls free on that, right? Because that was not allocated keeping pages in mind.
What do you mean?
So that place, the stolen memory.
This part?
Yeah, that part.
Yeah.
It was not kept with pages in mind, right? So it may span across pages.
Oh, yeah. It might be. So if it spans multiple pages, then you can end up. Suppose it spans 4 pages. Maybe it's possible that you can get only 3 out of them.
Yeah.
But it's okay. You can get 3 at least, right? Yeah. But it's possible that this part is less than 1 page size. Then you cannot get any free pages. But that's, yeah.
Because we did not track how many pages it span also, right?
You don't know, but you can calculate that in RAM steal memory. Every time you do that, you record how many size you allocate. You can do that. Yeah. Any other questions? Okay. So then what to store in each COMAP entry? So because the COMAP entry is supposed to represent the physical page, right? So naturally we want to state the physical page status, whether it's free or pinned to memory, or it's dirty or clean. I will explain this stats in later slides. So we also want to record where this physical page is mapped to user space. And why do we want this information? Why do we want to know where this physical page is mapped? Yeah. What? Swapping, yes. So suppose you are scanning the call map entry and you found out that there is no free pages. You need to kick out some page, right? By kicking out, you need to actually know where this physical page is mapped, because you need to modify that address space to indicate that this page is no longer there. It's swapped out, right? So you need to know this owner information. And also, how many pages were allocated together. This is mainly for allocated K pages, because it's possible that allocated pages allocate multiple continuous pages. So you need to know what's the chunk of that multiple pages. So when later on you free them, you can free them all instead of free one, right? And also other information needed by the paging algorithm, like the timestamp for first in, first out, or the access count, or the least recently used. So all kinds of information you can store in the call map entry. So this is the physical page state transition graph. So initially, all the pages, all the remaining free pages are in free state, right? So when we call kmalloc, which in turn is called allocated K pages, that page that becomes pinned into memory. We'll talk about why we need to pin kernel pages in memory later on. For now, you need to know that the kernel pages has to be in memory and cannot be swapped out. And later on, when kmalloc when kfree call free K pages, this page status from pin come back to free, right? This is one loop. This is for kernel pages. And for user pages is allocated by page alloc, right? It from free to 30. One question, why we mark it 30 when we first allocate a page? Because naturally, intuitively, it's kind of clean, right? Nobody have used it. Why we mark this page as dirty? What do you mean? What do you mean? No, that's not, yeah.
Is it because we fill it with kind of bogus values?
No.
And when they come,
No.
it's not there?
Because you want to write it to the disk for the first time, and it's not.
Yes, so what's the definition of dirty?
So when it is dirty, the content in the disk is not same as what we have in the
Yes, so dirty actually the meaning is twofold, right? First, if this page don't have a copy at all in disk, then it's definitely dirty, because when we choose to evac this page, we definitely need to write this page content to disk, right? That's why it's dirty. Second is that the normal dirty, right? Is so the page does have a content copy in disk, but the content is different, so it's dirty. In this case, it's in the first meaning, right? That this page has not have a copy in disk yet. That's why we mark it as dirty. And you may have a routine called flush, which just write the page content to disk. After this function, we can mark this page data as clean. Clean meaning that if you happen to choose this page as a victim, when you swap in, you can just safely discard it, because it already have a copy in disk. Right? It's clean. And later on, when you flush, after you flush the page to disk, user may touch this page again, may write some content, right? Which will make this clean page dirty again. And finally, if page free is called on this page, it returns to the free state, right? Yeah.
Do we need to do this for OS 161?
Yes.
Clean dirty, I mean, we can just swap out whichever page we can, right? I mean, do we have to maintain a...
You can. I mean, you can choose to not maintain the dirty and clean information.
Yeah.
Every time you swap out a page, you always write to disk. That's what we do. Yeah, that's kind of have overhead, because if this, so suppose this page is just a swap in and haven't been changed yet. If you choose to swap out that page, you actually don't need to swap out. You don't need to flush. You can just discard it. That's the advantage of managing the dirty and clean state of the page. Yeah. You also, of course, you can merge these two in one, like called mapped, or something like that. Yeah. Yeah.
When you're calling VM fault, it changes it.
VM fault is actually not a code. It happened when user try to touch a clean page. You need to make that happen. So when you flush a page to disk, you need to change the TLB entry so that a user cannot write to it unless trigger via TLB fault. So you got a chance to change the page state. Okay. So two things to note. First, page is dirty when first allocated, and second is that the kernel page is pinned to memory. Can never swap out kernel pages. And another thing is to know you need to differentiate between physical page state and virtual page state, right? So in user's virtual address space, we have virtual pages, right? First, all the virtual pages are unmapped, meaning that there is no corresponding physical page for this virtual page, right? And then user starts executing, touch some virtual address, trigger page fault, you allocate pages. At that time, that virtual page has a mapping or has a corresponding physical page in memory. We said that that virtual page is mapped, right? Later on, if you choose to swap out that underlying physical page, you need to mark that virtual page as swapped. So that when user try to access a swapped page, it can trigger page fault and you can get a chance to swap in the page, right? So when the virtual page, the state changes from mapped to swapped, what happens to the underlying physical page? I suppose I have virtual page mapped to a physical page, and your paging algorithm decided to swap out this physical page, right? You definitely need to change the page table to indicate that this physical page has been swapped. That's one thing you need to do, right? What about the underlying physical page? The status of the physical page has to be one of dirty and clean, right? It cannot be free, it cannot be pinned because it's user pages. And so what happens to the physical page? And first, to answer that, you need to, what?
It will become free, right?
Not necessarily. Why do you want to kick out that page? Because you want to use that page,
Yeah.
right?
Something else will replace it, right?
Yeah, you want to use that physical page for some other purpose, either for kernel page or for other user page. So either the physical page will either go to pin state, which we use for the kernel, or it stays in dirty and clean, just that the owner changed, right?
Content also.
No, what?
Content will change.
Content, yeah, definitely the content will change, yeah. So this is the transition of physical page and virtual pages. Everybody is okay with this? Okay. So to test your COMAP implementation, basically implementing COMAP means that you need to design the COMAP structure, write the allocated K pages and free K pages function. So after you do that, you can test them by two test programs called KM1, KM2 from kernel menu. And you want to make sure you pass this test before continue designing the user space and page table. Okay. So any questions on COMAP in general? Yeah.
I did try debugging the KM1 and KM2. It doesn't work allocate pages at all. The KMalloc has a sub-function called sub-allocate page, something like that, which is called on KM1 test. Only on the KM2 test is one allocate.
I think KM1 test will also involve allocated K pages. No?
It doesn't go into that.
Confirmed?
Yeah.
Well, I'm not sure. I need to check that. But KM2 is just a multi-thread version of KM1. So maybe you have too much memory. No, that's not the case. It must call allocate pages, otherwise it cannot allocate memory.
Within the malloc function, there is a subfunction that allocates. I guess it takes the memory from the kernel space. That's it.
You mean the allocate pages called RAM-steal memory?
I don't know how it works, but
Yeah.
I had a
Either way, the KM2 is used by the autowaiter. The KM1 is not run by the autowaiter. But KM1 should also test your call map. It's a single thread, so there will be no synchronization. That should be the case. Yeah. Okay. Yeah.
In virtual memory, you said too late fetching. Should we do that?
What do you mean?
I mean, you meant that virtual page does not map to physical page.
Okay.
Right now, as soon as we allocate virtual page, we allocate physical page as well. Should we stop doing that?
You mean whenever you allocate a physical virtual page, you always allocate a physical page?
Should we wait for page fault or?
Well, ideally, you should do lazy page allocation, meaning that you never allocate a virtual page unless user touch that.
Yeah.
Ideally, that's the way to do it.
Is it a problem? Do you recommend?
I don't know. Continue doing that and see if there is a problem. Yeah. See, ideally, you should do lazy page allocation. So today we're going to talk about this MIPS virtual memory, page table design, and user address space. So we know that we're dealing with 32-bit architecture, right? The virtual address space is 4 gigabytes. This is hard-coded by the hardware. So the hardware will trigger the virtual addresses into 4 regions. The first region is from 0 up to 0x8 the first 2 gigabytes, which is the user segment. Whenever the hardware encounters a virtual address in this region, the hardware will consult the TLB for the translation, right? The hardware will look up the TLB to find out what's the underlying physical address. This is the first segment. And the second segment is from 0x8 up to this. It's called kernel segment 1. It's directly mapped, meaning that so if you access a virtual memory in this region, the hardware will not look up TLB. Instead, the hardware will just by chopping, set the most significant bit to 0 and use that as a physical address. So in the process, there will be no TLB involved. It's directly mapped. That's why it's called directly mapped. It's cached as usual. This region is where our kernel lies in. Our kernel always uses virtual addresses inside this region, meaning that the kernel has direct mapping and kernel has view of all the physical memories, right? As long as the kernel know which physical address to access, they can always come up with a kernel virtual memory that accesses that physical memory. Okay, and then comes the second kernel segment 1 from from this address to this address. It's also directly mapped, meaning that if the hardware see a virtual address in this region, it will set the three most significant bit to 0 and use that as the physical address. Just that in this case, the hardware will not use the cache for this physical address. It's usually used for the bootloader or the I/O, do the I/O stuff. Because when the system is first put up, the cache doesn't work yet. So it may be beneficial to put some code in this region before cache works. So the code will set up the cache so we can jump to the kernel segment 0 and using the cache. Basically, it's used slightly in this OS, but most of the code in kernel lies in this virtual memory region. And finally, we have kernel segment 2, which is TLB mapped. It's still kernel address, but it's mapped by TLB. It's not used in this OS because once your kernel is also using TLB, something tricky may happen, right? When you handle a TLB fault, you may trigger another TLB fault. When you handle that, you may trigger another TLB fault. So it's very complicated. So it's not used in this operating system. So we will mainly use these virtual addresses in this region. Okay, this is how MIPS translate the virtual address. A common mistake is that MIPS, somebody may think that MIPS always use a TLB to translate the virtual memory. That's not true. It will depend on which region that virtual address lies in. Sometimes it will use TLB, sometimes it doesn't. Okay, so the one rule of thumb is that the CPU always use virtual memory. Right? Every address is issued by the CPU is virtual address. Right? It's a hardware's responsibility to figure out which physical address to use depending on the virtual address. For example, if the CPU issues this instruction, the hardware will know that, oh, okay, this is the user segment virtual address. I will use TLB to find out where the actual physical address is. So this part we will use TLB, right? If the CPU issues this instruction, the hardware will know that, oh, okay, this address is actually in kernel segment 0, which means that I do not need to consult TLB for the mapping. I just chop the most significant bit and use this as a physical address. Okay. Similarly, this falls into segment 1, and I use this physical address to do the load. This is in segment 2. Again, I use TLB. So these are all virtual addresses. The hardware will figure out how to translate the virtual address. And you may notice that there are 2 macros defined to help you do the translation. Because we always use virtual addresses in kernel segment 0 in kernel, we can translate between physical address and a kernel virtual address. So given a physical address here, we just add it by 0x h million, we got the kernel virtual addresses. Yeah.
I don't think
The second one is
K what?
the second macro there is not actually defined.
It's not?
I have to do it myself.
You can define it. Yeah. Well, maybe I define this, and I figured it's defined by some kernel. Yeah. The second is kernel virtual address to physical address. Again, given this kernel virtual addresses, we minus it by 0x at the median, we got the physical address, right? So one example usage of this mapping is that, so in the previous example, we know the first physical address, right? We want it to be the start of the call map. Right? Instead of directly assign first physical address to call map, we need to do the translation, right? Because this has to be a virtual address. Okay. Any questions on this in general? The address translation? Yeah.
So the reserved kernel physical addresses are already in that kernel space in the core map slide? So if you put it in the core map slide, you get a physical memory.
Wait, here, yeah.
Yeah, so that kernel will aggregate those
This,
are translated.
you mean the addresses contained in this region? Well, that's virtual pages. So the instructions here are accessing virtual memory.
I'm just thinking if, the kernel has some of those physical addresses that it can access from that bit shopping. So the core map can't necessarily be kernel address.
What do you mean exactly?
This is the physical memory, right?
Yeah, this is a physical memory from 0 to, yeah.
Right, so the kernel addresses are directly translated to segments of the physical memory.
Yes,
So those can't be used for user addresses, right?
it can be. A physical page can be mapped to user virtual address. So here in this mapping, you will notice that one page here can be mapped to kernel virtual address, can also be mapped to user address by TLB. This mapping ensures that the kernel has access to all the physical memory, so the kernel can give page to user. You can always map any physical page to the first 2 gigabytes.
There's only 512 MB of memory, right?
What?
How do you access the
How do you access?
KSX0?
User access that. So in user space, user access a user space virtual memory. It will trigger a page fault. You allocate the page.
What I meant is, let's say we want to use user space memory in kernel space without using TLB.
Without using TLB?
So for that we have KSX0, right? So we append everything, whatever we want with 8, and it will become user space memory. We can access directly.
Kernel can access user space memory. So suppose there is a syscall. Say suppose sysexec v, right? You know the program name. Kernel can read that program name, right? Because that, so if kernel issues user space address, that address will be translated by TLB. It's not who issued the address, it's what the address is. If the address falls into this region, then it always uses TLB. So inside the kernel, if you copy some memory from user space, that copy will use TLB.
No, our route was different. In AS copy.
AS copy.
We had to copy one user space address to another user space address, right?
No, actually.
No.
You need to copy the page content.
So in case of fork, you copy the child thread success space to parent thread success, sorry, parent thread success space to child thread success.
Yeah, AS copy.
Yeah, so at the time what do you do? That's what is question.
Yeah, so this is only
How do
512 MB,
you
right?
use it?
I mean, in OS 161 it is okay because 512 is the maximum.
Yeah.
But what if there is more?
Right now, it just use the first 508 megabytes
Yeah,
of memory.
In case it is more, how will KSX0 be able to handle that? That's what.
KSX0,
Yeah,
this one?
KSX0 is
Well, KSX0 can only map 512 megabytes maximum. If you have more than that, you want to use that, you need to use KSX1. Oh, sorry. KSX1 is still 512 megabytes. You need to use KSX2 to map that. Yeah, that will use TLB. Yeah. Any questions? Any other questions? Okay. So now we continue to page table design. So the kernel doesn't use page table, right? The kernel virtual addresses are directly mapped to physical address. So the page table is only for user addresses, for user processes. It's responsible for mapping the virtual address in create user segment to physical address. And it also responsible for maintain the page status, either clean, mapped, unmapped, or swapped, the permission. So when you design the page table, a few trade-offs to consider is that what's the memory overhead of the page table, right? If for each 4K page, you have a very huge page table entry, then the overhead will be large. That's what you want to minimize. And also lookup efficiency, because it's possible that the lookup is happen quite often. So you want to speed up the lookup time. And also as simple as possible for implementation purpose. So the first possible way to design the page table is you just use a plain linked list, right? For each virtual page or virtual address, you have a page table entry that contains the physical address in it, right? You can also store some other information here. Then finally, you have a pointer to next entry. So whenever you need to look up the mapping, you just traverse this page table or page table list and find out the mapping, and you fill the TLB for that. So advantage of this approach is that the linked list is quite simple. Everybody has learned that from data structure courses, and it's quite efficient in space, in that it needs at as 12 bytes per page can meet the purpose. So this is 4 bytes, this is 4 bytes. And if you're smart, you can compact this information to one of these 4 bytes, right? Because the last 12 bits will not be used, so you can use it for other purpose. So you can use at least as 12 bytes per page mapping. The drawback of this approach is that the look time is linear. In the worst case, every time you need to traverse the entire list to find out the mapping. The second approach is the classical two-level page tables, right? Jeff may cover this in the lecture. So briefly, we use some of the bits to index a page directory. This page directory points to the second level page table, and we use the second 10 bits to index that page table. We got the base of the 4K page. And finally, we use the offset to get the final physical address for that, right? So the advantage of this approach is that the lookup time is constant. No matter what virtual address you are looking for, you can always get it by at most 1-2 lookup, right? So the lookup time is constant. And in terms of space, it's also efficient. So for each physical page, you need 1-2 entries to store the mapping, right? But the drawback of this approach is that when user address space is sparse, in that user may not have that many virtual pages, this will potentially cause memory waste, because suppose user just have one virtual page. To translate that one virtual page, you need to allocate this and this, and there will be only one entry in this table that is used. All others are wasted. Right? So, but in general case, this advantage is still good in that it can provide constant look time, and the user address space is normally have multiple pages. So the amortized memory cost of the page table is reduced. Okay, this is two-level page table, and you can extend it by multi-level page tables. So you can further divide this virtual address to different regions and use different bits to index the page table and finally get the mapping. So it can still provide all constant look time and less wasted memory because each of the page table size is reduced. Okay, but the drawback is obvious. It's quite complicated to implement. It's totally up to you again to choose the design option. Yeah.
Why is the directory smaller? If you go back on the slide.
Yeah.
Why is the directory?
If you use 10-bit to index the directory, then what's the directory size? 2 to the power of 10, 1024 entries. Here you use 6-bit. What's the length of the page directory? 2 to the power of 6, which is 64.
Right, but for both directories, there's 6 bits. So like
Yeah.
the first one, say 32 right now.
Because we only translate for user address. The user address, the first bit is always 0. That's kind of a small trick, but ideally it should be 64. It should be the same size. But because in this operating system, the higher bit is always 0, so we never use it. So we can reduce this by half. Also in this case, this should be 1024, but you can make it as 512. Yeah. Any questions on this page table design? Okay. So finally, we go to user address space. So last time we covered what the user address space looks like. This is virtual addresses, and you want to store the page table, whatever page table you choose, either the head of the linked list or the page directory base, and the region information. You want to know how many regions are there. So in page faults, you can check if that virtual address is valid, and also heap and stack information.
Just one question. Do we really need that region info because we are not
If you think you don't need it, just don't save it. Later on, you will find out you need it. Then you come back, save it. Yeah, quite simple, right? If you think you don't need it, just don't save it. So in each of the address space function, ASCreate is quite simple. We just initialize the address space structure and then initialize whatever inside it. For in AS-defined region, it's an opportunity for you to store the region information. Also, it provides an opportunity to adjust the heap start point, because when you create the address space, you don't really know where the heap starts, right? So first you load this region, you can set the heap start to this point. And then you load the second region, you can adjust the heap start point to this. If you no longer load any regions, then this will be the final heap start point, right? Heap can grow upwards from this point, right? So AS-defined region is a place where you can adjust your heap start point. In AS-prepare load, you can set up the page table, or you can allocate the pages, but I don't recommend it. So you should allocate the pages in a very universal way, in that you only allocate pages when somebody is actually trying to access that virtual page. You may also want to change the page permission to be writable despite of the actual region permission. So even though that code region is only readable, you may also want to set it writable so that the load elf can write to it. Right? You need to write some content at the first time, then you can set it as read-only. Right? So these two pair of functions is kind of like open a backdoor for the kernel to load the address space. Right? This is open the backdoor so that the load elf can write some content to the memory. This is will close the backdoor so that we resume whatever permission it is. If it's read-only, then we set it to read-only. Then as define stack, very simple, just return the user stack top. As activate, invalidate all the TLB entries so that we can start load mappings from the current addresses page table. And as copy, you need to create a new address space structure and copy every page, including the page table structure and actual page. You can try to implement copy on write pages, but leave that to the last if you still have time after you finish the assignment. It will be quite tricky. And for ASDestroy, just destroy all the address space structure and free every pages inside it. Okay. So any questions on this address space? Yeah.
Can you go to the next? In ASCopy, what if the page is in file? Should we copy?
It depends on you. You can do some trick stuff like two mappings mapped to the one page on the disk, but you can also copy it, make it two copy. It depends on you. Right. Okay. So this is what we talked about this today, and the Guru will cover the TLB and page fault next week. Okay. Any questions? Well, that's it. Thanks.